Hi, today we're looking at section 7.9, which is natural logarithms and related exponential functions. So natural logarithms use what's known as our natural number, which is Euler's number, which is represented by this E. To get the natural number E, we take the following series to infinity. So 1 plus 1 over 1 plus 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 1 times 2 times 3 times 4 plus 1 over 1 times 2 times 3 times 4 times 5, and that series to infinity. So essentially, that gives us a number that's going to continue on forever, but the first several digits are 2.718, and that's equal to E. Now, on your calculators, that letter will be on your calculator programmed into memory, so you don't have to remember what these digits are. Now, a natural logarithm is defined whenever we see ln x. So this is the natural logarithm where we have a base of e. So we're using our Euler's number as our base of our logarithm. And this we refer to, like I said, as our natural logarithm. Now, if we have our natural logarithm of x equals y, then if we're changing that into exponential form, it becomes x equals our base of our natural logarithm, which is e to the power of y. We also have a restriction that x has to be greater than 0. Now, all laws of logarithms also apply to natural logarithms. So, for example, solve 25 is equal to 5 times e to 3x. So first thing I would do here is see if I can reduce either side. So I'll divide both sides by 5. So you've got 5 is equal to e to 3x. At this point, I'll change this into a logarithm to solve. Now, because we have Euler's number as our base here, we are going to use our natural logarithm. So we've got our natural logarithm of 5 is equal to our natural logarithm of e to 3x. Now, because these have the same base, that means that we have our natural logarithm of 5 is equal to 3x. At this point, to get x on its own, divide both sides by 3. So we have our natural logarithm of 5 divided by 3 gives us x. And that gives us 0.536 is equal to x. Next example, we've got solve 2 times our natural logarithm of x plus our natural logarithm of 9 equals 18. So first thing I would do is utilize my power law. So this becomes the natural logarithm of x squared plus our natural logarithm of 9 equals 18. Now we can use our product law because we have this addition here. So we end up with the natural logarithm of 9x squared equals 18. So at this point, I will change this into an exponential function. So this was base e, so it becomes e to 18 is equal to 9x squared. At this point, divide both sides by 9. So that gives us e to 18 over 9 is equal to x squared. Take the square root of both sides. And that should give us 2,701.028 is equal to x. Next example, we have negative of our natural logarithm of x plus our natural logarithm of x minus 2 equals our natural logarithm of x plus 2 minus our natural logarithm of 2x. So on each side, it looks like we can perform the quotient law. So this will give me my natural logarithm of x minus 2 over x. While on this side, we have the natural logarithm of x plus 2 over 2x. Now, because we have a single logarithm on each side with nothing else, and it's the same base, we can drop our logarithms, because if this side equals this side, and they both have the same logarithm happening, that must mean what's inside the logarithms are equal. So we've got x minus 2 over x is equal to x plus 2 over 2x. So first thing, I will multiply both sides by something that will get rid of the denominator on both sides. So I'll multiply both sides by 2x. So on this first side, these x's cancel out. So we've got 2 times x is 2x. 2 times negative 2 is negative 4. On this side, this 2x cancels out entirely with that 2x, so we get x plus 2. At this point, I would move this x to this side, and I'll move the 4 to the other side. So that gives us x is equal to 6. Okay, so next we have the exponential growth or decay formula using natural numbers and natural logarithms. So we have a, which is our final amount, is equal to a naught, which is our initial amount, times Euler's number to the power of k, which is our growth factor. If our k is larger than 0, our population is increasing. If it's less than 0, it's decreasing. And then t is our time period. Now, this can also be rearranged as our growth factor times time is equal to natural logarithm of our final population over our initial population. So we'll utilize this or both these formulas in the next example. So for example, the population of Japan was estimated to be 126.8 million in 2017. Japan has an average population decline of 0.2% per year. Suppose this trend continues to nearest 1/10 of a million, what will the estimated population be in 2030? Okay, so first thing we want to do is solve for our growth factor. So therefore, we will use our formula where our growth factor takes less steps to get on its own. So it's our growth factor times time is equal to our natural logarithm of a over a naught. Now, in this case, because they've given us a rate per year, that means we can, for this equation, use a time of 1 year. So time of 1 times k is just k equals our natural logarithm of, essentially this is our ratio of our present population over our past population. So if they've given us information here, so if we have 0.2 2% decline. That means that each year we have 99.8% of the previous year's population, which has a decimal of 0.998. So that's going to be representative of A over A naught, because that's our ratio of our current population over our past population. Now, instead of calculating this right now, I'll substitute this into equations later so I don't have to worry about rounding values off. So we now want to figure out what the population would be in 2030. So we have our A equals A naught times Euler's number to the power of our growth factor times time. So we've got A is equal to, we've got 126.8 million. I'm not going to write this out with all the zeros. Instead, I'm just going to put 126.8. And then because this is in the millions, our answer we get here will be in the millions. Okay, so times e to the power of our natural logarithm of 0.998 times our time, which we have 2030 minus 2017. So that will be 13 years. And that gives us a population in 2030 that's expected to be 123.5 million.